In this video, we focus on section 10.4, the error in Taylor approximations. Suppose we want to approximate the values of some function f(x) near axis A using the nth degree Taylor polynomial Pnx. This is near axis A. In order to know whether we have a good approximation, we need to look at the error between fx and Pnx. This error, we denote it as Enx. Of course, we want the size of Enx to be small, and we do this by finding an upper bound for the absolute value of Enx. The idea is that if this upper bound is small, then En has to also be small. We have the following error bound for Enx. It's also called the Lagrange error bound for Enx. For Pnx. So it says that suppose f and all its derivative are continuous. If Pnx is the nth Taylor polynomial, for fx about axis A, then Enx, its absolute value, is the absolute value of fx minus Pnx less than or equal to m over n plus 1 factorial s minus a, the absolute value, to the power n plus 1, where the absolute value of n plus 1's derivative is absolute value less than or equal to m on the interval between a and x. So this is called the Lagrange error bound for Pnx. We find an upper bound of the absolute value of Enx. Next, we look at an example to show how to use the Lagrange error bound. So this example, give a bound on E sub 4 where E2x is approximated by P4x about x0 on the interval x greater than or equal to negative 0.5 less than or equal to 0.5. So our function is E2x, right? So we let fx is E2x. We use the Lagrange error bound. The Pnx, n is 4, right? We approximate E2x by P4x. So we need to find this m. So to find m, we need the fifth derivative. So we know fifth derivative of e2x is still itself. And we know e2x is positive all the time and increasing. e2x is positive and increasing. So we have its fifth derivative x, its absolute value is e2x, the absolute value. Right? So on the interval s between this negative 0.5 and 0.5, so it's less than or equal to e2.5. This is the square root of e. This is less than 2. So on this interval, the fifth derivative is bounded by 2. Thus, we can take m is 2, which gives e4, the absolute value, is the function es minus p4x. So this less than or equal to, so it's m over n plus 1 factorial. So it's 2 over 5 factorial. Then absolute value x to 5, x between negative 0.5 less than 0.5. Thus we have for x between negative 0.5 and 0.5, e2x is approximated by 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And the error is at most 2 over 5 factorial is 100, 0.5 to power 5. This is less than 0.00006. Of course, for smaller values of x, we get smaller errors.